Hello everyone, welcome back. In this lecture, we shall see meshing and types of boundary conditions. We shall start with meshing. Meshing involves dividing a complex geometry into simpler and manageable parts, and these are all called cells or elements. The governing equations are solved in the elements for CFD and FEA analysis. If you see in this image, the complex geometry is transformed into multiple smaller elements or cells. We can solve the governing equations in these cells and we will get a unified solution. Okay. Next we shall see the types of mesh elements. The first one is 2D mesh elements. Here there are triangles and quadrilateral elements. Triangular elements are flexible and ideal for complex shapes as it can easily fit into any complex body. Next, quadrilateral elements are harder to generate for complex shapes, but it is suitable for simpler geometries and you can easily control the flow of elements in quadrilateral type. Next we shall see 3D mesh elements. Here there are tetrahedral or hexahedral or pyramid elements. Sometimes there are prism elements too available. Okay. Hexahedral or cubical elements are commonly used in structured meshes. It provides high accuracy and computational efficiency. You can easily place the hexahedral elements in simpler geometries so that you can control the number of elements easily and you can solve the boundary layer properly. The next is pyramids or prism elements. These are all less frequently used. They are used as a transition between hexahedral and tetrahedral elements. Prism elements are commonly used in boundary layer elements called as inflation layers. Next, let us see the types of boundary conditions. This is quite important. Let us focus. There are different types of boundary conditions in CFD solvers. The common ones are shown here. That is inlet, outlet, wall and opening. Inlet represents the flow entering the domain and it can be given in terms of velocity, mass flow rate, total pressure, total temperature along with the flow direction and magnitude. So by default, inlet represents the flow entering the domain and the outlet represents the flow leaving the domain. We can specify static pressure, velocity or mass flow rate near the outlet conditions. There are some more parameters which can be used at the outlet condition, but these are all common terms. Okay, next is wall. It defines the interactions at the solid surfaces. And there are different types of wall boundaries, that is no slip wall. Here the fluid velocity is 0 at the wall. This is the actual case. And there is slip wall. It means fluid can slide along the wall and there is no shear stress involved near the elements around the wall. Okay. Next we can specify heat transfer options in the wall, that is it can be either constant temperature or constant heat flux or adiabatic wall. We can also specify moving walls which are commonly used in turbo machinery applications. Okay. The next one is opening. So it defines both inlet and outlet conditions. Here the flow is bidirectional and you can specify either opening pressure or static pressure condition for opening type boundary conditions. If you are using opening pressure, it represents total for inflow and static for outflow. And if you are choosing static pressure, it is always static. Okay. These are the common boundary conditions used in CFX. Next, we shall see few more boundary conditions. That is symmetry condition, periodic boundary condition and interface conditions. We can use symmetry conditions for geometrically similar objects. Here, there is no flow or heat transfer across the plane. This is important. It is used to reduce the computational effort by simulating a part of the domain, example half of the domain or 1/4 of the domain. So in this image if you see, this object can be symmetrically divided into 4 parts and we can choose any one part and then apply symmetry condition on the common faces. By this method, we can solve 1/4 of the domain and we can get the results for the whole body. So this is called symmetry condition. The next one is periodic boundary condition. This can be used in domains where the flow repeats over the entire domain section. It saves the computational time for repetitive geometries like turbo machine application or heat exchanger applications like fin and tube and also in similar repetitive geometry applications. For example, in this image, the entire impeller is not solved but a single periodic sector is chosen and then CFD is solved only on this single periodic domain. It can be used for rotational periodic domain as well as translational periodic domain. Okay, this is about periodic boundary. Okay, next is interface. Interface conditions are used between two zones or two mesh bodies. That is, for example, either in fluid-solid interface in conjugate heat transfer application or fluid-fluid interface or between two solid domains, etc. So interface boundary conditions are used between two zones. Okay, these are the common types of boundary conditions. We shall see Y plus and turbulence models in the next lecture. Thanks for watching this video. I will see you in the next lecture.